This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Alright guys, can you all hear me? Yeah, I think there's something wrong with the microphone. Whenever I on the microphone, there's a bit of a feedback. But all of you can hear me, right? I hope. Okay, that's good. And I hope you guys at home can hear me as well. Right, so we are at lecture 10 now. So we are halfway through potential flow, right? And we only have a few more weeks until the end of potential flow, right? And then you don't have to see my face ever again if you don't want to. Okay, so let's do a quick recap of what we did last week. So we looked at different types of flows last week. So we had when you have a source plus a uniform flow, alright, we had a half Rankine body, right, and hopefully you know how to sketch this flow. Right, we also looked at when we have a source plus a sink. Okay, and you should be able to show that the streamlines for this flow, a source and a sink, are circles. Right, next we looked at a source plus a sink plus a uniform flow. Okay, and this is the full Rankine body. After that, we looked at a source plus a sink, right, when it's superimposed on top of each other, right? And what we get is a doublet, right? So we call a source plus a sink, which is superimposed on top of each other, a doublet. And you should be able to derive the stream function of a doublet and to sketch the flow of a doublet, right? Next, we had a flow of a doublet plus a uniform flow, which gives you a flow over a cylinder, right? So, if we know our stream function for that flow, we can calculate our velocities, okay? And using Bernoulli's equation, we were also able to derive the pressure distribution about this flow, right? This flow over a cylinder, okay? Right? And then I showed you this plot here of the pressure coefficient against theta, which is just the angle on the cylinder. And you can see that the flow is symmetric, right? And it looks something. Oops. It looks something like this, right? So it's symmetric. So we have our streamlines, which are similar at the front and at the back of this cylinder, right? So the streamlines diverges, right? And then it converges back at the back, converges together at the back of the cylinder. Okay, but in real life, hopefully you know that, or in most engineering application flows, right, which are at high Reynolds number, flow separates. Okay, and actually what happens is something that looks like this, where you have turbulent wake at the back of your cylinder. Now, but if you look at the first half, right, or the upstream flow, right, you can see that the flow over this cylinder is actually not too bad with our, it's not too bad compared to our potential flow solution, right? You can see that the streamlines, let's say at the first half of our cylinder, looks very similar to the higher Reynolds number case, right? And you can see that the agreement is actually quite well, right? Up to some angle here, okay? And then after that, the flow separates and then we get very, very different results. But, I mean, the results which we get from potential flow, which we have made quite a few assumptions, right, which is two-dimensional, incompressible, and it's also inviscid, right? It shows quite reasonable, I guess, reasonable predictions, right, up to a certain point along this cylinder. Okay, and if I was to show you another example, let's say we have flow over this car here, you can see that the front part of the car, I guess, looks quite similar to the potential flow solution, up to some point where at the back of the car, once the flow separates, you're going to get very, very different flow features. But up to some point, the potential flow solution is not too bad. Right? So I guess we need to know the limitations of potential flow. Okay? It's not very good at capturing flow separations, but in certain areas it is able to predict reasonably the flow features. Okay, so to sketch these flows, hopefully by now I've been nagging to all of you the steps, right? You need to first find the stream function. Okay, and once you know the stream function, you can find the velocities. And I want to find my stagnation points, basically where velocities are 0. And from that, I can then derive an equation for the separatrix. And I can then sketch this flow. Right. Also, we have derived our Bernoulli's equation. Therefore, we should be able to use it to find the pressure coefficient on the surface that we're looking at. Okay. Also, remember that when you're sketching, that your streamlines cannot cross each other. Okay. And we can replace our streamlines with solid boundaries because velocity perpendicular to our streamlines are 0. Stagnation points are also saddle points. Basically, we have 2 streamlines coming into a saddle point and 2 coming out from the saddle point. And when sketching, it's always good to consider the near and far field of the flow, right, from the origin. So in the far field, normally the flow is going to be dominated by the uniform flow, and close to the source, for instance, your flow is going to be dominated by the source sink or whatever flow that you're looking at. Okay. Right. So today we're going to learn another different function, which is called the velocity potential, phi. Right. And I told you last week that phi is actually quite similar, or it's very similar to psi of a stream function. Okay. So let's find out more about this function phi. Right, so remember our stream function psi was derived or was defined so that it automatically satisfies continuity. Okay, so if I substitute my definition of psi back into continuity, right, you can see that it automatically satisfies it and I get it to be equal to 0. And if I want to satisfy my momentum equation, I have to ensure that my flow is irrotational, or basically the Laplacian of psi is equals to 0. Okay, so that's for my stream function. Now it's possible for me to define this function called the potential function, which now instead of satisfying continuity, it is defined so that it satisfies the irrotational. So it basically means that phi is defined so that it is irrotational. Okay, so if I substitute u d phi over dx and v equals to d phi over dy back into this equation here for vorticity, it should automatically give me 0. Okay. Hopefully that should be obvious. If I substitute this into here and that into here, that automatically should give me 0, right? So the flow is irrotational, 0 vorticity. Okay, and if I substitute d psi dx into, del phi del x over del u over del x, and if I substitute del phi del y into del v del y, okay, you can see that to satisfy continuity, the Laplacian of phi has to be equal to 0. Okay? Yep, so all I've done, I've just substituted these two terms back into continuity to get this. Okay, so the Laplacian of phi has to be 0 for continuity to be satisfied. Right, so this, I guess this table here summarizes my stream function psi and my potential function phi quite nicely. Okay, so on the left hand side here I have continuity at the top, right, and at the bottom there is irrotational or vorticity, right. So basically when the flow is irrotational, momentum equations are automatically satisfied, right. So my stream function automatically satisfies continuity, and it's defined so that u equals to del psi del y, and v is negative del psi del x. Okay, whereas my potential function is defined so that it automatically satisfies the momentum equation, or it ensures that my flow is irrotational. Okay, and if I define it as such, then my velocity u is going to be equal to del phi del x, and v is going to be del phi del y. Okay, so my stream function then satisfies the momentum equation when the Laplacian of psi is equals to 0. Okay, and my potential function satisfies continuity when the Laplacian of phi is equals to 0. Okay, so I told you this stream function and potential function, they're quite similar. They're like siblings, right? They're like brothers and sisters. Okay, they're very similar yet very different, polar opposites at times. Is everyone following so far? Yep, good. All right. So let's look at a simple uniform flow, okay, which you all know before, which you all have seen before. So u equals to u infinity as it's moving. The flow, uniform flow, is moving from left to right. Okay, and v is just 0 because there's no vertical component in this uniform flow. So using our definition of a potential function, okay, I can then integrate u here with respect to x and v here with respect to y to find phi. Okay, so if I integrate the equation on the left here, I'm going to get phi equals to u infinity x plus f1, which is some function of y. And on the right hand side, just integrating del phi over del y equals to 0 will give me del phi equals to f2, which is some function of x. And hopefully you can see that this equation is compatible when this here is equals to this term here, and f1 here is just equals to 0. Okay, so you should get phi equals to u infinity x. Okay, everyone understand so far? Yep. And just to compare, the stream function for this uniform flow is equals to u infinity y. Now, these blue lines here are lines of constant psi, which are my streamlines. Can anybody guess how lines of constant phi would look like? Perpendicular? Very good, right? So it will be perpendicular to our streamlines. Okay, so our lines of constant phi in red will be perpendicular to our streamlines. Right, we can also derive the potential function for our other basic flows, such as a source. Okay, so you remember that a source has some radial velocity, but my azimuthal velocity is 0. Okay. And I hope you all know how I got this equation here. Right, this is just basically deriving it from the conservation of mass. Right, we did it a couple of lectures ago. Right, so UR is just equals to my flow rate, Q divided by 2 pi R, and U theta is just equals to 0. Right, you all? Alright, you guys should know that. And for this case, it will be easier to use our definition of a potential function in cylindrical coordinates. Right, where UR equals to del phi over del R, and U theta is equals to 1 over R del phi del theta. Okay, you all should know how I get this. It's basically the similar steps which I've done for our stream function a couple of lectures ago. Remember when we compared the sine and cosine terms? Right. Similarly, you can do for the potential function, and you get a relationship for UR and U theta. Okay, so I'll let you guys do that at home, but you all should know how it looks like. Okay, so all I'm doing now is just substituting UR with del phi del R and U theta with 1 over R del phi del theta. Okay, and to find my potential function, all I have to do is just integrate, right? So integrating both equations, I'll get phi equals to theta over 2 pi log R plus F1, which is some function of theta. And on the right hand side, I'm just going to get F2, which is some function of R. Okay, so again, comparing my constants, this one here has to be equal to this term, right? And this one here is just 0. Right, therefore, phi equals to Q over 2 pi log R. Okay, and I just put my stream function psi to compare. Alright. So you all should know, I guess, how to express a source in potential function and also in stream function. Right. Right, and your lines of constant phi, okay, will be perpendicular to lines of constant psi. Right, so it will be circular. Right. Okay, so similar to a source flow, a sink flow just has a negative in front. Okay. So it's now negative Q over 2 pi log R. Okay, so you all, hopefully you all can see that lines of constant phi are perpendicular to lines of constant psi, right? So let's prove this, because you guys don't trust me, right? So let's prove this together. So let's consider a small change in phi and psi. Okay, and psi and phi. Okay, so I want to consider some small change. D psi and D phi. Okay. So some small change in psi is going to be equal to del psi over del x dx plus del psi over del y dy. Okay, and I know my definition of psi is u equals to del psi over del y, and v is going to be del psi over del x. Don't forget the negative in front there. Okay, so all I'm going to do now is substitute that into here and this into here. So I'm going to get d psi equals to negative v dx plus u dy. Okay, and that has to be equal to 0 for lines of constant psi, right? So what's this equation here? Hopefully you all remember. Streamline, right? So that's the equation of a streamline. Very good. Okay, and I can rearrange this as well so that I can find my gradient. So del y over dy over dx for a line of constant psi is going to give me v over u. Okay, I'm just rearranging it. And I'm just going to call this 1. Okay, now we can do the same thing for phi. Oops. Okay, so for phi, I'm going to get d phi. It's going to be equal to del phi over del x dx plus del phi over del y dy. Right? Because phi is also a function of x and y. Okay, and I know my definition of a potential function is u equals to del phi del x and v is del phi del y, right? No negative in my v term, okay? So again, if I substitute this into here and this term here into here, I'm going to get d phi. D phi equals to, d phi equals to u dx plus v dy. Okay, and that has to be equal to 0 as well. So it's line of constant psi. Yep. Okay. So if psi is a constant, if phi is a constant, d phi is equal to 0, right? Okay, and again I can rearrange to find my gradient dy dx. So dy over dx for line of constant phi is going to be negative u over v. Okay, everyone happy so far? Right, so what I'm going to do now is I'm going to multiply this gradient here, right, this gradient here with this gradient here. So I'm going to take dy over dx for line of constant psi multiply with dy over dx for line of constant phi. Okay, and hopefully you can see that will give me v over u, negative u over v. So that's just negative 1. Oh, what did I do? Now, if I have two gradients which multiply to give me negative 1, what does that tell me? Right? So from calculus, you should know that the multiplication of two gradients which are equals to negative 1 means that it's always perpendicular. Right? So multiple of gradients equals to negative 1. Therefore, it is always okay. Everyone okay? Yep, okay. So going back to the slides. Oops. Okay, so we know our relationship for our stream function and potential function in Cartesian coordinates. You should also know their relationship in cylindrical polar coordinates. Okay? Right, and if I compare psi and phi in Cartesian coordinates, right, if I look at the velocities u, right, I can then get a relationship between psi and phi. Okay, so del psi over del y equals to del phi over del x. Okay, and if I compare my velocities v, whoops, you should be able to see that del psi over del x equals to del phi over del y. Okay, just by comparing my velocities u and v. Right. Similarly, if I compare psi and phi, so if I compare my velocities ur and u theta, okay, I'll get a cylindrical polar relationship between psi and phi. So I'll get 1 over r del psi del theta equals to del phi del r. And if I compare my velocities u theta, I'll get negative del psi over del r equals to 1 over r del phi del theta. Okay? Right, so many students ask me, Leon, do we get a formula sheet in the exam? And then I'll tell them, no, you don't get a formula sheet in the exam. Alright, so you all should know this by heart. Okay, you should. Hopefully, by the end of this course, you have it at the back of your finger or wherever, right? Not, don't bring a cheat sheet into the exam, but at the back of your mind, you should know all this. All right, and I guess the reason why I don't have this formula sheet in the exam is because if I give you the formula sheet, then most of you are able to reverse engineer the question, and you should be able, and you can then answer the questions, right? But I don't want you to reverse engineer your answers. Okay, so there's no formula sheet given, right? But we do, if you look at the past year exam questions, you should see that if you know the basics of this subject, you should be able to attempt it quite easily. Alright? But anyway, you all hopefully should remember these relationships: stream function, potential function, and the relationship between them. Okay? Or if you don't memorize them, at least know how to derive them so you can use it in the exam. Okay? Alright, so now I know a relationship between psi and phi. So this means if I have a stream function for, let's say, this flow of a cylinder, I can then find my potential function very easily, right? So I know that psi and phi are related by this relationship here in cylindrical coordinates. Okay, so all I have to do then, well, I can use the equation on the left or on the right, but I'm just going to use the equation on the left. If I use the equation on the right, I should still get the same answer. So I'll let you do that yourself at home, but in today's lecture, we'll be using this relationship here. Okay, so all I have to do then is just substitute psi into here, which will give me this equation here. Right. Now, looking at the left-hand side of this equation here, I'm going to differentiate, oh wait, hold on a second. I'll put this into my equation here. Oh no. I'm going to differentiate sine theta first, I guess. Alright, so I'm going to differentiate sine theta, so they'll give me cosine, right? Cosine theta. Okay, and I have this 1 over r term here, which I'm going to put into my equation here. So this will give me a squared over r squared minus 1, hopefully, yes. Right? So I get something like this. So to find my potential function, all I have to do then is just integrate it with respect to r. Okay, and if I integrate this, hopefully you all know how to integrate this. This is quite easy. So I should get negative a squared over r, right? And if I integrate negative 1, I'm just going to get negative r. Okay, so this is your potential function for a flow over a cylinder. Okay, and this is in cylindrical coordinates. So go back home, try and use this relationship here to derive your potential function. You should end up with the same answer. If not, then you might have done a mistake. Right, so now I have phi and psi for this flow. Okay, and these red lines here are lines of constant phi, okay? Right, which are always perpendicular to your streamlines. Okay, and the flow field inside of your sphere, you can see is a bit interesting, all right? But we can cover it up with a solid boundary, our cylinder, okay? And you can see this flow field over our cylinder. Right, so what's the physical representation of these lines of constant psi? Or phi, sorry. So these lines of constant phi, right, or equipotential, they are analogous to contour lines. Right, so you can see in this contour map here, the closer the lines are, right, the steeper your topography is, right, as compared to the left-hand side here. So similarly, lines of constant phi, all right, so if you look at these lines here, you can see that these lines of constant phi are much closer than here, right? So what does that tell you? Which the flow is it faster here or is it faster here? It's faster here, right? Because your lines of constant phi are close to each other, right? And you can see that here your lines are quite far apart. The lines of constant phi are quite far apart, therefore your velocities here are actually smaller. Okay. Right. So hopefully all of you have written a code to plot streamlines. Has anyone not seen the assignment yet? Okay, so hopefully all of you have done some MATLAB coding, I hope, if you all been to the workshop. How many of you do not have a partner for your assignment? A group mate? Alright, if you guys are looking for a partner, you guys can maybe huddle together in the front and can do it together or something. Alright? But yeah, so hopefully all of you know how to plot streamlines, okay? Using either the RK4 method or Euler's method. So how can we then modify our code so that we plot lines of constant phi? Right, so currently we are tracking streamlines, but to track lines of equipotential, we need to make sure that they are perpendicular to our streamline. So we have to change our code a little bit. Right, so I have a fluid particle here. Okay, and for a streamline, dx dt is just equals to u, and dy dt is just equals to v, right? And my particle tracks the streamline. Now, if I want to plot lines of constant phi, right, it's going to be perpendicular to that. So now, dx dt is going to be negative v, right? Right, dx dt now used to be u, but for lines of constant phi, it's going to be negative v, okay, and dy dt is going to be u, right? So all I have to do is just change my code so that I plug this relationship in, okay, and I should be able to release particles to lines of constant phi. All right, now you have learned what phi and psi are. I'm going to add one more concept, which is the complex velocity potential, W. Now, if you look back at the relationship between psi and phi, okay, we can express del psi del y equals to del phi del x, and negative del psi del x equals to del phi del y. Now, I told you that phi and psi has a very special relationship, right? And when you can write a function in terms of this, okay, they are known as the Cauchy-Riemann equations. Right, so I can replace psi here with b, right, some function, and phi here as a, some function, arbitrary function a and b, right? So when I can express it in this form here, these are known as the Cauchy-Riemann equations, named after Augustine Cauchy and Bernhard Riemann, right? And Cauchy is so famous that he has his face on a stem, right? So he's a very famous mathematician, I believe, right? So the Cauchy-Riemann equation basically says that if my function a and b can be written in this form, I can then write a and b as a complex solution, right? So w equals to a plus ib. Okay, and that's all it says. Right? And we know that a and b are functions of x and y coordinates. Okay, and z is a function of x plus iy. Right, which is a complex number. Right? So z I can replace, sorry, x plus iy with z, which is a complex variable. Okay. Right, and I can write my complex variable in terms of r, e, I, theta as well. Right, everyone seen this before? Everyone knows, right? Right, so going back to our stream function and potential function. So psi and phi, they have a very interesting relationship, all right? They are shucks. They are a Cauchy-Riemann equation, sorry. Right? Therefore, I can rewrite psi and phi as a complex solution, right? So I can write W equals to phi plus I psi. Okay, and this is known as the complex velocity potential. Okay. Right, so you guys don't trust me again, so we're going to show that psi and phi, right, the brothers and sisters psi and phi, they actually automatically satisfies Cauchy-Riemann equations. Right, I got a couple of notes here, you don't have to write it down, I'll just upload it for you guys later on. Maybe we'll prove it in the next lecture. Okay, but just to summarize, so remember that psi satisfies continuity, right? And phi satisfies irrotational flow, right? So vorticity is equal to 0, which also means that we are satisfying the momentum equation. So the cool thing about the complex velocity potential is that W therefore satisfies all governing equations, right? So W, which is equals to phi plus I psi, automatically satisfies all governing equations, right? For a two-dimensional, inviscid, irrotational, incompressible flow. Okay, and if you don't, and since you guys don't believe me, in next lecture we'll show that indeed if I start with W equals to phi plus I psi, right, I should be able to recover this relationship here. Okay, and if you still don't believe me, come to Wednesday lecture and I'll show you. All right, that's all for today. Yes. You don't have a group member yet? Alright, and those of you who don't have a group member and who is looking for a group member, just feel free to come in front here. Yeah, so I'm not sure who has a group member or not, but yeah, if there's a few people who haven't, maybe you guys can get a group together. Yeah, okay.
Question about the
So the
F1. Yeah, F1.
oh, yep.
We did the experiment. The stagnation pressure plus the flash pressure, the leading gauge is very low. I mean, in theory, we should know that the stagnation is higher than but I asked to operate. I didn't know, I didn't understand.
Oh, really? Oh, I didn't.
So in every point we have something. But the stagnation pressure and the leading edge, it's 10 point something.
It's less.
Less.
Yeah. I don't know. I haven't done the F4 lab for so long, so I can't really remember. Sorry. But so he said, so your stagnation pressure is lower than free stream.
Yes.
So are you measuring? Are you sure you're measuring stagnation pressure, or are you measuring static pressure?
Yes. Because maybe the beta tube, maybe it's they switch it, but the reading edge 15. It's number 15. It's also smaller. The reading edge should be higher, right?
Yeah,
Is this right?
I can't remember. I can't remember the F4 lab good enough
Yes,
to advise you.
In general, the leading edge should be higher.
It should be, but yeah, I don't know. Are you measuring the? Yeah, it's you have to look at the difference, right?
Yes, yes.
Yeah. Sorry. Maybe send him an email.
Yes, and he said it should be higher.
Or maybe try Morgan. Try sending to Morgan. Morgan might know better. I really can't remember. So
Yes.
sorry.
Thank you.
Okay. Yep. How are you? Yep.
One thing, what you teach today for the rigid body, for the adult body, basically this has the half rectangle body for the like when we flow the outflow, I mean the pressure line here, the current line is going farther away. So there is the higher pressure, higher pressure, and also for the when the other solid body.
Oh. So if so that one you're talking about my pressure coefficient, right?
Yeah.
So my pressure coefficient.
Is that related to that one? What you explained this one?
No. This is different. No. So this is it's not the same.
It's not the same.
So this one, right?
Yeah,
if it's
this
closer,
one.
you see it's closer, means the
Yeah.
velocity is higher.
This will be higher.
Yep.
Okay.
So you remember, if you look at the gradients of
Yeah.
you see here, right?
Yeah.
So it's like a contour line. So if your contour lines are very near,
Yeah.
means it's very steep, right?
Basically, okay.
Yep. But in here, if your contour lines are very close to each other,
Close to each
your
other,
velocity is very high.
Velocity very high. Okay.
And then when it's far away, the velocity
Velocity
is
lower. And also, isn't the straight line is basically Q, right? Flow rate, volumetric flow rate.
sorry,
This straight line is basically volumetric flow rate.
the cross section of the
Cross section, yeah.
Yep.
So when the velocity is lower, is that area is higher?
For streamlines or
Yeah.
lines of equipotential.
Like equipotential.
Oh, so for equipotential, right? Basically,
Yeah.
if your lines are further apart,
Yeah.
it just means that your velocity is slower. So it tells, but the flow rate, that one is
Yeah.
between streamlines.
Between straight lines.
Between streamlines, so that's
Oh.
different. Yeah.
Okay. So the previous one, CP is nothing related to it.
No, it's different. Yeah.
Okay.
So this is not CP. This is not really
That one is not included the velocity, just only the pressure.
for CP.
Yeah.
Yes. So from your velocities, you can derive CP using Bernoulli's equation.
Okay. Yeah. The first one is like for what you do for the Bernoulli equation is really good. Like for the everyone you give the step by step. I mean for the what we have to find straight line and also sine and also find the UMP velocity and then stagnation point and then going to the step by step so we can easily follow and do the start. So can we get that kind of thing in the previous just like I mean for every Hamas equation or something like
Well, Helmholtz is different, right?
yeah.
Because this is derivation.
Yeah.
Yeah, so it's the steps are different. Yeah, but typically don't memorize the steps, but normally it is as such. Yeah, for Helmholtz and all that is different. That's a derivation.
Yeah.
So you need to know the steps or the tricks
Yeah.
to simplify the equation. So whether you multiply it with dx or you differentiate it with dx. So yeah, It's hard to write the steps
I mean,
down.
yeah. Somehow I do it differentiation and some kind of integrating and also substitute in the equation.
Yep.
After that, just in the stop. And also because like the what we have to like this, I really appreciate what you did here for that kind of thing.
Or this, because this one is quite structured,
Yes,
but the
yeah.
derivation is a bit different. You need to know what you want to exclude. So like when Helmholtz, right, you want to exclude the dp term.
dp term, yeah.
dp, yeah. So what you have to do, so you have to remember. And different people remember it differently, so I don't want to. Yeah. But if I can make
Yeah.
as structured as possible, I'll try.
Yeah.
I'll try help you out.
Yeah, thank you so
Okay,
much.
alright, no
Yeah.
problem.
Okay, sorry. I don't quite understand how to implement this change of this direction. Because I think if you
So here, right, all you have to do is, if your doublet is a negative, right, instead of getting a flow over a cylinder, you get a very weird flow.
yeah, I mean, since it's for symmetrical, how do you judge whether it's this direction or this direction?
So it starts back from our derivation of a doublet. So if you go back to... So go back to lecture... Was it lecture 9? I can't remember. 9. Okay, we started with... so we had our source on the right and our sink on the left. So we started derivation as such, right? So that's why it's moving this way at the top bit. Right?
Oh yeah, okay.
So it's going this way. Yep.
So at this situation, if I move the source a little bit, like a little bit to the left, the direction will change.
Yes, because this would change. Because instead of alpha A minus alpha B, you'll be alpha B minus alpha A maybe.
Okay.
Yeah, so that's why you get.
Thank you very much.
Okay.
And one more thing.
Yep. Yep.
In the assignment,
Yep. Is that a mistake?
uh,
Oh no, don't tell me it's a mistake.
Can we use MATLAB for solving this and
Oh no. Yeah, you have to use back. I think the calculus. I can't remember. So solving linear equations, I think. Yeah. Don't you, so you can use MATLAB to check,
okay.
but you need to show the steps how you integrate and all that to solve it. Yeah. Okay, no problem.
That homework question that we had that day, I got this one result.
You guys did the homework. Nobody listens to me and do homework. Nobody. Okay, but you were good.
I just want to know these two. How do we get these two? From which equation do we get these two? So this was the source was sink plus reverse uniform flow, and we had to show this, that if this is equal to this, the stagnation points are 0, 0, and these two were the other two.
So we have got this expression and this expression. You got the expression, but how do we relate it to the condition?
There's a condition, these two conditions.
It should be here, right? So you know that it so you got the equation here, right?
Yeah.
So if this one here is a real number, right? So this is greater than 0, this here is greater than 0, right? Then it lies on X.
Oh, okay.
Okay. Understand? So if let's say this is less than 0,
Okay, so that's it?
that's imaginary, so you don't have solution.
Thank you.
Okay, no
So
problem.
it was easy or?
Hey, yes. Yeah, I guess you can, but then there's no concession given. So that's not a problem. Sure. Okay. Yeah, it's still okay. Okay. Yeah. You sure you don't want to find someone to help? Oh, do you guys? Okay. Yeah, that's fine. It's okay. Yeah, sure, no problem. Alright. Okay. Okay. Don't copy, alright? Don't plagiarize. Don't plagiarize. Okay.
F1 lab?
Oh, I can't remember the F1 lab.
No, not F1.
Oh, no?
lab.
Okay.
It's,
Oh, this one.
Yeah.
Okay. Oh, what? What
That's
random is this?
250.
Hey, it's shading.
Yeah.
It's not supposed to shade, right?
No, it's not. It's like parallel. Yeah. So I have no idea.
Yeah, I think that's fine. But it looks nice.
Yeah.
And you're using Lambda 2.
Lambda 2. That's black and Lambda 2.
Okay.